Hi guys, hope you're doing well this evening. Um, can you guys confirm for me that you can see my screen and hear me? Thumbs up. Here we go. Perfect. Alrighty, so welcome to session 2 of exam prep training. Okay, as per usual, raise your hand or unmute if you have a question. You can keep your cameras off. So today we've got a hell of a lot to get through. I think I have something like 60 slides in this deck, so it's huge. It's a lot of slides, but I've tried to minimize how much text there is just to make it a little bit more spread out, a bit more palatable. But we're going to go through crosstabs, Z transformation, sampling distribution of means, and both of the one sample tests. So it's a lot of explaining to do. And there's also some theory woven in there, but some of the theory doesn't require a lot of explanation, so it won't take too long to get through. I am going to keep moving with the content, so if you do have a question, if you're a bit lost somewhere, please speak up. Okay, as promised, the solution for yesterday's Pearson's R. So yeah, I remember someone gave me their covariance and said it was 179 point something. So yes, that was correct. And your final Pearson's R should have been 0.76, which is positive and strong. Okay. Did anyone not get this? Do you want a second to look at the solution? Or are you good to move on? Give me a thumbs up if you're good to move on. Cool.
Sorry, I can't find the thumbs up button, but I'm fine to move on. Where's the button? I don't see it.
It's probably in your bottom bar.
Oh, I got it. I got it. Yeah.
Okay, cool.
Yeah.
Awesome. Let's go. Okay, so we're starting today. Those who joined me for the SPSS training, I've already been through this with them. But one of the most common problems that people tell me they have with this course is that they read a question and they're not really sure what they actually need to do with it. So this is my little procedure for breaking down the question. And I promise you, every single calculation, every single analysis in this course is unique and does use specific language to indicate what it wants you to do with it. Okay. So these are the 3 things you always have to ask yourself when you're reading a question, or things you have to identify. How many variables are involved in the analysis? What's the level of measurement of those variables? So it doesn't matter if it's nominal or ordinal, okay? I want you to think of, is it categorical or is it continuous? Okay, because that's how you make your decision. And then the final thing is, what are the keywords that scream at you in the question? So like I said before, language is not used accidentally or unintentionally. They use language very intentionally in this course. Okay. So like yesterday with Pearson's R is always 2 variables. They both have to be, in this case, they're both ratio, but they both have to be interval or ratio. Okay, the key word that's used for Pearson's R is relationship, correlation, and association, those 3 words. And that gives you a Pearson's R. Okay. Now today, we're going to look at something quite similar in terms of keywords, right? So 2 variables, you're also looking at a relationship between these 2 variables, right? Key difference is the level of measurement. When you're doing Pearson's R, your level of measurement is interval or ratio. When you're doing a crosstab, your level of measurement is going to be nominal or ordinal. Okay, so it's categorical variables, and that leads you to do a crosstabs. Okay. Remember that there are certain words that are also always associated with like the tests of significance. So the word significant or significance is indicating inferential statistics. So it's telling you where to go. If it mentions hypotheses, then, there you go. If it mentions hypotheses, then it also is indicating inferential statistics and is telling you to go in that direction. Okay, so with the descriptive statistics, like Pearson's R and crosstabs, none of those words are going to appear either. Okay, so a crosstabs question is very simple calculations, very simple conclusions. Okay, because this is not a test of significance, our conclusions are going to be really basic and are going to be very visible. So whenever we get a crosstabs table, when we get a cross table like this, okay, our independent variable is always going to be in the columns. So here, female and male, right? Those are categories of the independent variable biological sex. And your rows, so 7 to 10 hours, 6 to 7, less than 6, those are ordinal categories, right? For number of hours of sleep. I didn't put all the details here, but just so you know. Okay, so IV in columns, DV in rows. And when they ask you what are the relevant percentages in a crosstab, it's always the column percentages. Okay, what that means, column percentages, is when I calculate this percentage for females who sleep 7 to 10 hours, to get this percentage, I go 3 divided by the column total, 11, multiplied by 100 to get the percentage, and I get my percentage. And then I need to do that for all 3 of these categories. So 4 divided by 11 multiplied by 100, and so on and so forth. And then you do it for the male column as well, so that you have all your percentages. Okay, once you have all of your percentages calculated like this, then calculated in columns, then you start comparing horizontally. Okay, so what we're looking at here is, of those people who sleep 7 to 10 hours, right? 27.27% of the women sleep 7 to 10 hours, whereas 66.67% of the men sleep 7 to 10 hours. So the really obvious conclusion there is that the males are sleeping more than the females are. Okay. And then you can see here with 6 to 7 hours, the percentage for the females is higher. And same for the less than 6 hours, the percentage is higher. So your simple conclusion is literally the males are sleeping more hours than the females in this sample. Nothing more complex than that. Is anybody unsure about crosstabs? Are we all comfortable with crosstabs? This is the extent of it for now. Yeah. Okay. And crosstabs looks exactly the same in SPSS output as it would if you did it by hand. Okay. The only difference is that the output would have already calculated your calories, my gosh, percentages for you. So when you're reading these percentages, they've already been done. So you just need to compare these percentages going across like so. And an example conclusion for this particular one. So it's looking at different game platforms, okay, and how well they score with the critics. And you would say that PC and Sega games score the highest from critics, whereas Nintendo games score the lowest. Sony and Microsoft games score similarly. And that's it. Honestly, interpreting crosstabs is just testing your ability to see high and low percentages for a particular variable. Okay. We're good to go. Not much else to say here. I think so. Okay, finally, we're starting to head into our inferential statistics. Okay, so inferential statistics, just a little refresher. Now we're starting to talk more about populations. Now we want to make generalizations about populations. Okay, so the population is obviously the larger group of units of analysis that you'd like to generalize about. The sample is the smaller group of units that you take from the population to be able to analyze. Okay, your sample design. Okay, this is something you learned in ISSR. It's the procedure that you use to select your sample. So did you do probability sampling? Did you do simple random sampling? And you would have learned that your sampling procedure makes a huge difference in terms of how representative your sample will be of the population, right? So probability and simple random sampling guarantee that the researcher doesn't have any kind of bias in selecting cases. Okay. And then sampling bias is when your sample does not represent or reflect the population accurately because of a flawed sampling procedure. So if you use a sample design that is more for qualitative research and you use it for quanti, that will present a sampling bias. Okay. Or if the researcher had more say in who was selected and who was not. Now, sampling error is very different from sampling bias. Okay, so both of them speak to your sample not completely reflecting the population perfectly, okay, or accurately. But the difference is that sampling bias is due to a flawed procedure, meaning it could have been avoided, the researcher made a mistake. Whereas sampling error is inevitable, meaning there's no way that we can take like a simple random sample and it perfectly reflects the population. So we actually include sampling error in the math. We account for it and it becomes the standard error, which we'll come back to later. And then finally, your tests of statistical significance. Okay, those are the tests that allow you to go from just sample numbers to generalize about populations. Any questions about this terminology? No, lovely. Okay, guys, now it becomes even more crucial to know your symbols. Okay, so the reason, especially for the standard deviation, okay, it is going to be the key difference between choosing a t-test over a z-test. Okay, it's got to do with what standard deviation did they give you? Did they give you sample standard deviation, which is S, or did they give you population standard deviation, which is sigma? Okay, you need to remember your differences between your population mean, your mu, versus sample mean. Okay, because they're going to both appear in the same formula and you can't mix them around. Okay, starting with the normal distribution. Okay, so there are 4 characteristics of our normal distribution. One is that it is unimodal. Okay, just one sec. Okay, it's unimodal. Okay, uni means one mode. We know what the mode is. One mode, one peak. Okay, it only goes up once. Second is that it's symmetrical. Okay, because right in the dead center here, we have our mean, our median, and our mode, right? And our median cuts the data into 50-50. So it's completely symmetrical with 50% of the data lying above the center and 50% lies below the center. Third, it's asymptotic to the x-axis. Okay, what that means is that if we follow this blue curve and we follow it all the way, it's heading towards the x-axis, even though in this image it starts to touch the x-axis, okay, it's actually asymptotic, which means that this blue line can carry on until infinity and it will never touch the x-axis. Okay. And then the last thing is that this is theoretical, meaning that most real-world data is not perfectly normally distributed, okay, because that's just highly unlikely. But we use the theoretical normal distribution to base the math, and then we have a little bit of leeway with real-world data with how normally distributed it needs to be for the math to still hold. Okay. Any questions about these 4 characteristics? Okay. Okay, like I said, if your mean, your median, and your mode are dead center, which means they are all 178 centimeters, we're looking at the height of adult men in the US. Okay, so your mean population mean always sits in the middle, and that means that the data is 50-50 on either side. Okay, so we know that 50% of men in the US are shorter than 178, and 50% are taller than 178. How do we know that? The median. Okay. So do you see that if we start talking about probabilities, right? So what is the probability of selecting a man from this population? And what's the probability that he'll be taller than 178? Well, at this stage, it's 50%. That is the probability. Okay. And in the tails is where your outliers or your extreme values will lie. So there are very few men who are really short and very few who are really tall. Okay, most of the data is around the middle. Okay, we also know something about the standard deviation that again allows us to divide the normal distribution into percentages. So because we know that 68% of our data lies within one standard deviation of the mean, if we were to ask this as a probability, it would be what is the probability that randomly selecting a man from this population with a height of between 170 and 186 would be 68%. Okay. So now that we use the median and the mean and the median serve the same function here. And we have these standardized percentages for the standard deviation. We can use them to basically standardize X values and be able to get probabilities for any X value that we want. And that's what leads us into the Z transformation and the sampling distribution of means. Okay. So the way this question is asked, the Z transformation. What percentage of adult males in the US have a height of more than 190? What is the probability that a randomly selected adult male from this population has a height of more than 190? What is the chance that Okay, so what I'm drawing your attention to here are your keywords. So this language doesn't appear anywhere else in the course. Okay, these are probability questions. And as you can see, the answer that they want from you in all of these cases is a percentage. Okay, so this should draw your attention to Z transformation and the sampling distribution of means. Okay, these are lovely questions because it's an easy formula. They're easy to get right. Okay, as long as you can identify them correctly. Okay, so your first step when you get a question like this is always to draw the distribution and actually mark the area that they've asked about in the question. Okay, so you would just draw the curve. You always put your mu, your population mean, in the center. They'll give it to you. You can write your standard deviation somewhere, doesn't really matter where. And they've asked for the area of more than 190. So 190 is higher than 178, so it's towards the right. And it's the area that is above 190 into the tail. Okay. So if we look at our formula, what we're doing essentially with this formula is that we're taking an X value, 190, okay, and we're standardizing it to become a Z value so that we can get a probability from it. So the X value is, oh, sorry, wrong one. So the X value is always the number that was given in the question itself. So the 190. Your mu is your population average. And of course, your sigma is your standard deviation of the population. They will give this all to you, easy peasy. And then you pop it in your formula. I don't know why I didn't show the formula here. It's a bit strange. Okay, don't mind me. I didn't put the formula here. But if you were to put it in here, so 178 minus, 190 minus 178 divided by 8, you would get your Z value. It's so strange that it's not here. Of 1.5, I believe it is. Okay. Yeah, there it is at the top. Sorry, couldn't find it on the right-hand side. Okay, there's your formula. You get a Z value of 1.5. Then you go to your Z table to find your corresponding percentage. You always look for this Z value in the A column. Julie, you raised a hand. Yes. Come at me.
Yeah, I have a question about the formula.
Sure.
Can you go back to the last slide? Because is the standard deviation, is that just because it's 8, is that just calculated with the standard deviation formula? Or
No. So great that you asked, because this is important. Guys, is this symbol, sigma, does it represent population standard deviation, or does it represent sample standard deviation? You tell me.
population, right?
Population, absolutely. Do you ever have population data that you can use to even put into a formula?
Oh no.
Think about an entire population,
Yeah,
like
no.
all Erasmus students. No. Because in the standard deviation formula, you actually have to enter individual
Yeah.
scores from the sample, right? So we never calculate population SD.
Mhm.
It's only possible for samples. So one, giving you that whole spiel is more important for a bit later. But no, this will always be given to you. Population
Oh, it's given.
is always given.
Oh, okay.
Yeah.
Okay, thank you.
Sure.
So is everything I need for this calculation always given?
Always.
Okay.
Yeah. Even if you look at what's involved in the formula, right? Your population mean, you can't calculate that. You don't have population data. Same for standard deviation. And then X value, well, the X value is part of the question. They have to give it to you. So it's all there. Okay. Once you got your Z value, you're going to go into your Z table and look in your A column. As you can see in the table, we've got A, B, and C, and then it repeats itself because the Z table kind of just does this when it gets in its numbers. So we look in the A column. Sorry, I didn't do this in the right order. A column, and we look for 1.5, which is here. It'll circle it in a second. And then once we found our Z value, we need to align it with either the number in the B column or in the C column. Okay. Now I want you to look at the B column and C column description. Do you see B says area between the mean and the Z value, right? And C column says the area beyond the Z value in the tail. So if we go back to the previous slide, this red area that they asked about, is that area between the mean and Z, which would also be the X value of 190, right? Or does it go out into the tail? It goes out into the tail. Does it not? You can see that. That's why it's really important to draw this when you get this question. So because it's the area that goes into the tail, that is the reason that once you've found your Z value, you choose the C column. Okay, there's your Z value. And the number that's in the C column that's aligned. And you can see this is in a decimal form, so it's 0.0668. You need to convert it into a percentage, which you can just do by like multiplying it by 100. And you get your final percentage. Okay. Your conclusion always uses the same words that were used in the question. So 6.68% of adult males in the US population have a height of more than 190 centimeters. Is anyone lost so far? with this? We good. Lovely. Okay, so choosing between your B and your C column is going to be an endless dilemma for you, but don't worry, there is actually a way to get used to it. So we look at this one. Where's my color? There we go. Lovely. We look at this example. What percentage of adult males have a height of more than the mean, but less than 195? Okay, so you draw your distribution, you put your mean in the middle, you mark 195, because that's the number in the question, and they ask for the area between those two numbers. Okay, do you see now the area does not go out into the tail? Now the area touches the mean and touches the number. Okay, so you do your formula as usual. Your X value is 195, what they gave you in the question. Your population mean, 178, and your sigma is still 8. It's the same question. Okay. Oops. Why is it not her? One sec, guys. There it is. Okay, sorry, it's all a bit late. So you put your, do your formula and you get a z-value of 2.13. You have a look in all your A columns until you end up with your 2.13. And this time, instead of choosing the C column, we're going to choose the B column because it's the area between the mean and the z-value, which you can see visually. So your final answer is that 48.34% of adult males in this population have a height between 178 and 195. Everyone comfortable so far? Lovely. Okay. Now let's look at this. Okay, now we have a special situation where it's not just a case of between the mean and a number, and it's not just a case of, more than a number out into the tail, where we actually have an area that's asked about that crosses over the mean. So this one is what percentage of men have a height of more than 170, which is below the mean, but less than 192, which is above the mean. Okay. So remember, our only options in the Z table is the B and the C column. Like, we have to work within those parameters. So because of that, we have to divide this area into two parts so that the green part is between mean and Z, and the purple part is between mean and Z. So we can do B column for both of them. Okay, so what that means, also you can see we've got two X values in the question, and that means we're going to be doing this formula twice, okay, each with a different X value. Now, please, as you can probably gather, is that once you've done these two sections separately, you're going to add them together to get the total area. Don't do that. Don't add the Z values. Okay, you need to wait. You need to get two separate percentages, and then at the very end, you can add the percentages. Never add the Z values. Okay, so if we do this one, that. Okay, we look at the two at the top. So here we use the X value 170, here the X value 192, and we get Z equals -1 and Z equals 1.75. Just a note that whenever you get a test statistic like Z or T or whatever, that's negative, okay? Don't worry about the negative when looking at the table, okay? We treat it as the absolute value. So we basically just treat it like 1. Not -1. So let's start there. We look in our A column until we find 1, which is there, and we pick B column. So the first one is 34.13%. Okay. Then for the second one sec, let me get everything on screen. Lovely. Okay, the second one is 1.75. So we find that down at the bottom, and that corresponds with 45.99%. Add those two together, and you get your total area. Okay. Is everyone comfortable with this? Yeah, cool. Just a note, I put it in the slide there, is that when you're doing this adding situation, the C column is never a possibility, okay? You only work with the B column in these situations, which you can see visually on the distribution as well. Okay, so in some cases we add and in some cases we subtract. What does it look like visually when we have to subtract our percentages? Looks something a bit more like this. So if they ask a question, what percentage of men have a height of more than 170, but less than 173? Okay, so it's this tiny little area. And you can see that the area they ask about, it doesn't touch the mean at all. So it doesn't cross over the mean, doesn't touch the mean, and it doesn't go out into the tail either. Okay, so you can see, again, like B column, C column, neither really works. Okay, so there's only one method to be able to do this. First things first, we actually need to find the area between the mean and 170. Okay, so it's this large area here. That's first step. And for that, we use the X value of 170. Okay. Then for the second step, we need to find this area that's uncolored, right? And it's between the mean and 173. Okay, in that case, we'd use 173 as our X value. So after getting the larger area and the smaller area, right, we can take the larger, subtract the smaller, and the difference will be the green area that we're looking for. Okay. So let's do our two X values, 170 and 173. Okay. Same process as usual to get our two percentages. Did I not do the solution? I didn't. Lol. Okay. I think I was in a rush today, guys, with this slide. So yeah, basically you do this formula twice, right? You get your two percentages, and then you always take the large percentage and you subtract the smaller percentage. Okay. Any questions about the subtraction? Okay. So those four scenarios, in terms of what it visually looks like, are the only four scenarios. Okay, you're never going to get anything else. So very easy to go about this question and get it right. Okay, and that's pretty much it for our Z transformation. If you have any questions about this, they might come later. But for now, we're done. Okay. And that leads us into the sampling distribution of means, which is a mouthful. Okay, it's also the sampling distribution of means questions are also probability questions. Okay, so they look very much like the Z transformation questions, and there are a few key differences that I'm going to point out so that you can identify which one to do. And the formula for the sampling distribution is similar to the Z formula for the Z transformation, and is actually the basis of your one sample Z test. Okay, now I'm going to tell you a little story. This is a hypothetical distribution. So usually with a normal distribution, what we've plotted on that graph is raw data, like individual X values from a sample, like Matthew in the sample was 173 centimeters tall, and we plotted 173, and we plotted everyone individually, and that's a normal distribution. With the sampling distribution, basically, it's a theoretical or hypothetical situation where, let's say you have 10,000, an Erasmus population of 10,000 people. Okay. Hypothetically, if you were to take a sample of 100 people out of that population, and you calculated a sample mean for them, and then you did it again, you took another 100 people from the same population, calculated their sample mean, and you kept taking samples of 100 people until you'd sampled everybody. Okay, so how many hundreds in 10,000? 100. Hope my math is correct, please. Okay, so basically you'd end up with 100 samples of 100 people each, which means you'd end up with 100 sample means. If you were to plot them like you're plotting a normal distribution, so instead of X values, now you're plotting sample mean values on a distribution. That is what the sampling distribution of means is. Okay. And if you were to calculate a mean of all the sample means, you end up at the true population mean, which sits in the center of the distribution. Okay. So that's the whole story about sampling distribution. Just so that you understand it in terms of like what it is. But you're not going to be asked to explain that. It's just for funsies. Okay. So I mentioned the first 3 bullet points. And then for your sampling distribution of means, what changes is that your standard deviation is on its own no longer what we want. We want standard error. Okay, so basically what we're doing with making it standard error is we're taking standard deviation and we're dividing it by the square root of n. Okay, why n? Why is n involved? N is sample size, right? So I want you to think about sampling error, what I spoke about before, where it is inevitable that our sample is not going to perfectly reflect the population. Okay, so think about what scientists do to minimize error when it comes to generalizations. Okay, one of the simplest and most intuitive things that we know that they do is they sample as many units or as many people as possible. Okay, if you read a research study where they only sampled 10 people and they want to make a generalization about the entire population that those people belong to, you're not going to believe it. You're going to be like, 10 people? Surely that cannot represent an entire population. As soon as you increase your sample size, so 1,000 people, 10,000 people, you know, the credibility is getting higher and higher because you've sampled more people. Okay, that's what's happening here with n and standard error. Okay, when n gets bigger, sample size gets bigger, your standard error decreases. Okay, your error decreases. You become more accurate. Okay, and why do we need that at this stage is because now we're actually starting to get towards the inferential stats. Now we do want to generalize about populations. We have to include in the math that the sample size will affect our accuracy level. Okay, does anyone have any questions about this at this stage? It's going to come up again, but I realized that formula was not on screen.
So the formula, the one on the, like, with the standard deviation sign, is the formula for the standard error.
Yes.
And the Z is for the Z.
A sampling distribution of means.
Okay.
Yeah.
Okay.
So the standard error formula, you can see that it's embedded in the formula for the sampling distribution. Do you see it at the bottom? Sigma divided by square root of n. So standard error is not usually calculated as a question on its own. It's embedded inside of the formulas, in inferential formulas. Okay, and what you should notice is that the formula on the right-hand side for your sampling distribution means is exactly the same formula that you will use for your one sample z-test. Okay, not the same question. Okay, don't get ahead of yourself to the one sample test. We're not there yet. Yes, Julie.
So you, sorry, in questions you don't really use the standard error formula on its own. Like you only use it embedded in the sampling distribution of means formula.
Yeah, pretty much. And I mean, like, it's always a possibility that they could say, please calculate the standard error. But generally speaking, it's part of another formula that you're already using.
Okay.
Yeah. And they do like you to calculate it first. Like when you're doing this formula, for example, on the right-hand side, they do like it generally when you calculate the standard error first, and then you do the rest of the formula with it.
Oh,
I
okay.
think it makes you a bit more accurate. It reduces error.
Yeah, okay,
Yeah.
makes sense. Yeah.
And what does the formula with the z exactly tells me? Like, tells me about the sampling distribution of means.
It does, yeah. So we haven't actually gotten to an example question, but the sampling distribution of means is almost identical to the Z transformation, what we just did. Okay, it's also probability questioning. The difference between them is going to be the formula used. So before, if you remember, our formula was Z equals X minus mu divided by standard deviation, right? Whereas now, instead of standard deviation, we have standard error. And instead of the X value, now we have a sample mean. Okay, this is what I was talking about with on a regular normal distribution, our distribution represents X values, individual scores. Yeah. Whereas our sampling distribution represents sample means plotted. Okay. But don't worry, we're getting ahead of ourselves. This is not the only slide on it. Okay. So I want you to actually pay attention to the both block at the bottom of the page first. So the question that they ask you for both Z transformation and sampling distribution of means is going to be, what is the chance? What is the probability? What percentage of cases? Yada, yada. It's like identical question. Okay. Both of them use a Z formula to be able to standardize the value and produce a Z value. Z transformation has that X minus mu over standard deviation. Sampling distribution uses the one sample Z-test formula. Okay, you put your numbers in, they'll give you the numbers. You put your numbers into your formula, you get your Z value, you look up the Z value in the Z table, and you find a corresponding percentage, and you conclude with that percentage using the same words as the question. So very, very similar. So what's more important is what differentiates them. For your Z transformation, it always asks you about an individual case or score. So it'll say, what percentage of cases, what percentage of adult males in the US have a height of more than, okay, they're talking about men, like individual men. Like, what's the probability of selecting a random man from this population, and his height is more than 174? Okay, so they're talking about individual males. Whereas for the sampling distribution, the keywords sample mean are going to appear. Okay, so they're not talking about drawing an individual, they're talking about drawing a sample mean. And they will also give you N. Okay, so if you remember the Z transformation formula, N was not involved, not in the formula. They had no reason to give it to you. For the sampling distribution, let me see if I can go back. You can see now, because of standard error, N is in the formula. So you need it. And so they will give it to you. Okay. We're going to do a couple of examples later on where you differentiate between these two. But even the word sample, there's no mention of that with the Z transformation. It's all population. Okay, so this is the kind of question you get. Given a population distribution with a mean of 22 and an SD of 2, so that's population mean and population SD. If we would draw one sample from this population, N equals 10, what is the probability of obtaining a sample mean of above 23? Okay, so you see it's the same question and you follow the same process. So you start by drawing the distribution, okay? You mark your population mean as 22 in the center. 23, right? That's the sample mean number that they've asked about in the question. You mark it. And it was everything that's above 23. So it's this little area there. So just by looking at this, you should already know you're going to be selecting the C column when you look it up. Okay. And you put it in the formula. Hold on, I missed it. There we go. Sorry. So there's the option up there on the right-hand side to do your standard error first, which could, like I said, reduce your risk of making a mistake, but it's really up to you. Your sample mean is the 23 from the question, right? Sample mean of above 23. And of course, your mu is 22. That was given to you. Everything will be given to you. You find your z value of 1.59, and in the z table, that corresponds with the C column, 5.59%. Okay. And your conclusion, just write it all out again. If we would draw one sample, n equals 10, from this population, the probability of obtaining a sample mean of above 23 is 5.59%. Okay. Same process, just pay attention to the keywords, because that'll change which formula you use. Any questions about this so far? No? Good start. We're doing well. Okay. Back to a little bit of theory around standard error. So this is what it looks like when you have a larger or a smaller standard error. So I want you to think of standard error as just error, okay, inaccuracy. What we want is a small standard error, because that means low error in generalizing about the population. Okay, so on the right-hand side is what low error looks like. And you can see that the normal distribution is a little bit skinnier. And that means that we're just being a lot more accurate with how it's distributed around the mean. Okay. Whereas on the left-hand side, it's almost like we're giving it room. There's like room for error because our standard error is larger. Okay, so this will make a bit more sense when we do the test of significance. But basically, if you're running a test of significance and you had a large standard error, it would make it much more difficult to reject H0 because the distribution is way more spread out. Okay. But it's not super important for now. What I really want you to remember about the standard error, in terms of like a theory question, is that when your sample size, your N, gets larger, okay, you sample more units, your standard error is going to get smaller. Okay. Okay. Bit of an early break, but that's okay because we have a lot of practice questions to get through today. So we might have a longer practice session, depending. So yeah, guys, take a break and I will see you back at 7:30. All right, guys, are we all back? Lovely. Appreciating the thumbs up, guys. That's good communication. Alrighty, now for the tests of significance. The very first one is the one sample tests. Okay, so when you're breaking down a question, okay, and to get to narrow it down to a one sample test, you will notice that there's only one variable involved in the analysis. That variable is measured as interval or ratio. And your keywords are usually things like based on prior research. It'll include either in the actual text or in the questions that follow the text. It'll have the word significance or hypothesis, or basically any of those words that we associate with the tests of significance. Okay. So just to give you an example of how you would narrow it down, if you're reading a question and there's only one variable, okay, and you can already see that it's about a test of significance. Cool, one variable, test of significance. Your only options are the one sample tests or the chi-square goodness of fit. Okay, but something we know about the chi-squares is that they are exclusively nominal ordinal tests. Okay, so that is excluded if we have interval ratio. Yeah. So when you're left with the one sample test, you've got your one sample z-test and your one sample t-test. What is the difference? Because these two are almost identical. It has to do with whether or not you know your population standard deviation. Okay, like I said earlier, you are never able to calculate a population SD. Okay, so it's either given to you, like in the question on a silver platter, or it's not given to you. Okay, so if it's given to you, you do a z-test. If it's not given to you, that means that you either have to use the sample SD, which they give you, or they'll give you sample data and you have to calculate the sample SD, and you would use a t-test in that case. Okay. Okay, hypotheses. All of your tests of significance involve hypotheses. And for each test of significance, you've got a basic structure of the hypothesis. Okay. And what we include in our hypothesis, what we're usually testing, is got to do with a population parameter, which is the mean. Okay, so for the one sample test, we're testing a mean. Same for the two sample t-test, same for the ANOVAs. Okay, they are always about populations, hypotheses. That's why if you see the word hypothesis, it has to be about inferential stats, tests of significance. Okay. And we use a test of significance to determine the likelihood that a hypothesis about a population parameter, such as the mean, is true. Okay, so if we look at the bottom, our H0 is called our null hypothesis, and this is our baseline of knowledge. Okay, it's our starting point for our research study. Basically, when you do your own research, you're going to read everything and anything that any other researcher has written about your topic. Okay, so all the previous research done on your topic. That is your baseline. That's what helps you establish what your H0 is. Okay, so if all the previous research about sleep says that people, like adults between 18 and 40, sleep 7 hours on average per night. Okay, all previous research points to that. That would be your H0. That the average of hours of sleep is 7 hours. Cool. Your H1 is what you actually want to test or what you actually want to prove. It's called the research or the alternative hypothesis. Okay, this is where you do your own study, you have a sample mean, and you're trying to find if your sample mean is different enough from the old previously known population mean to warrant saying that the old population mean is no longer true. or no longer valid. Okay. a quick word about your hypotheses here. So, you never prove your H1 directly. Okay, it's almost like you're always proving H1 by disproving H0. Okay, so it's all about rejecting H0 or retaining H0. Okay, and your H0 has the basic structure. Your H1 always follows the same structure. Okay, so if your H0 is that the population average equals 7, your H1 has to follow that. So the population average is not equal to 7, something like that. And of course, your H1 can be either directional or non-directional. Okay, so I don't know if we talked about this, but maybe in the SPSS training, when you have a non-directional H1, okay, that literally means no direction. So if your H0 is at the mean is 7, a non-directional H1 says that it's not 7. Okay, so that's pretty vague, right? We don't know if it's less than 7, and we don't know if it's greater than 7. It's just not 7. Okay, so it hasn't specified a direction. Whereas if it is directional, then it specifically states that the average is greater than 7 or it's less than 7. Okay, so how do we decide to reject H0? Okay, so what threshold do we use? Like, what point does it get to before we can actually say that H0 is no longer true? Okay. This is our level of significance, or our alpha, which is the 5% or the 0.05 that we're always referencing with our p-value. Okay, by making our alpha 5%, what that means is that we're capping the probability of making a mistake at 5%. Okay, so basically that guarantees 95% accuracy. Okay. We're going to come back to the alpha as well in a second. Okay, to keep it simple, when our p-value in SPSS is lower than the alpha, we would reject H0. I'm going to show you all this on a normal distribution in a second. Okay, so the p-value is how we reject H0 in SPSS, how we do it by hand. So these hand calculation steps apply to all of the tests of significance that you do by hand. So the one sample tests and both the chi-square tests. It's a little bit different for regression, just because the regression hand calculation question is just phrased very differently. So you start always with your H0 and your H1. Then you calculate your test statistic using the appropriate formula. Okay, this is what gives you your obtained value. Okay, so the obtained is always what you calculate. Then step 3, you look for a critical value in the appropriate table. In that table, it requires that you know your alpha, which is always 5%. Sometimes you need to know your degree of freedom, such as in the T table. And you need to know whether your H1 is directional, one-tailed, or non-directional, two-tailed. Okay. And then step 4, once you have your obtained and your critical value, you compare them side by side. If your obtained value is larger than your critical value, you reject H0. And this is true across the board with all of the hand calculations. Okay. Okay, so we're coming back to the alpha in a second. So we look at our normal distribution, right? Our population mean, which we know based on previous research, is sitting in the center as usual. Okay, when we do our own new study and we get a sample mean, we're trying to figure out where on this distribution would our sample mean fall. Okay, So this should start sounding a little bit like the sampling distribution of means, right? It's like, what is the probability of obtaining a sample mean? Well, that's kind of what we're doing. We're looking at what was the probability of getting our sample mean, okay? And if that probability is low enough, meaning it's so unlikely that we would get this sample mean, that means that it's so far away from the old population mean that the old population mean must not be true anymore. Okay, so we're basically looking for where is our sample mean? Is it here? Okay, you can see here it's still quite close to the old population mean, or is it in the tails? Okay, also called the rejection region. The rejection region is where your alpha sits. Okay, so if our alpha is 5%, that means that we want our probability of getting our sample mean to be lower than alpha to be able to reject H0. That should start to sound a little bit like the p-value in SPSS. When p is lower than alpha, we reject H0. Okay, we want our probability to be small. Now, this particular normal distribution, you can see that there's a rejection region in each tail. Okay, why is that the case? Because we're dealing with a non-directional H1 in this scenario. Okay, so if it's non-directional, that means we don't know if it's going right or left. We don't know if it's greater than or less than. We have to account for the possibility that it could be in both sides. Okay, but we only have we have a 5% alpha in total. That's all we get. So if we have to account for both sides, our alpha actually has to be split in two so that both sides get a little bit. So each side has 2.5% alpha, which we'll talk about a little bit more as we go along. But that's what it's showing you. The rejection region in both sides is a non-directional test. Okay, if we look at our hypotheses basic structure here, for our one sample tests for both of them, the H0 is that the population average of the variable is equal to a number. Okay, that number, okay, will always be given to you in the question. It is the old population mean that we know based on prior research. Okay. Your H1, if it's non-directional, is going to say that it's not equal to that number. If it's directional, it's going to say that it is greater or less than that number. Okay. Anyone got any questions on this at this stage?
So the sample z-test, does it have to do something with the z transformation? Because it kind of like throws me off. Like, is it one big thing or is it like two separate procedures?
I get you. So it's all linked in terms of like the logic and the math, but for your sake, for your needs, they are two separate questions. Okay, so the z transformation and the sampling distribution of means, they're asking a probability question. They just want to know what is the probability of obtaining this value, and they want you to give them a percentage and be done. The one sample z-test serves a different purpose, so it's a completely different question in practical terms. So yeah, to keep it simple, let's leave it at that. Does that make sense, Julia?
Okay, yeah, if it's two different things, I can separate it.
Yeah, two different things.
Can I also ask something about that?
Mm-hmm.
So will they ever like maybe do A and B, and in A we need to transform like z-scores, or like two z-scores, and then in B we need to transform the not transform but compute the one sample z-test
They totally could
with those
actually.
values?
Yeah, they totally could.
Okay.
So I think I made like a little practice exam a couple of years back where I did that. where I basically used all the same values, the same population mean, the same everything. I just asked 2 different questions. So that's why I really emphasize the key words or the key language that's associated with these different questions. So for the Z transformation and the sampling distribution, the way they ask the question is so predictable. It's what is the chance? What is the probability? Or what percentage of cases, right? They want you to respond with a percentage. Whereas a one sample Z-test is not going to ask that question. They're going to give you a bunch of information, and then they're going to say, which test of significance should you use? Formulate your H0 and H1. Compute the test statistic. Okay, so that all indicates that it's a one sample Z-test. Does that make sense?
Thank you, yes.
Okay, and if you look on the left-hand side here, our formula for our one sample Z-test is identical to the sampling distribution of means, because the sampling distribution is our basis, our mathematical basis, but separate questions, same formula. Okay, don't get that mixed up. I believe in your formula sheet, they only present this formula as the one sample Z-test formula. So it's up to you to just remember that it's also the formula for the sampling distribution. Okay. Oh, I copy-pasted stuff from other lectures, so that's why things aren't appearing on my timeline. So if we look at this, assume that we formulated the H0, that the average happiness among the population of EOR students is 6. Okay, so they've given you a population average. Population average equals a number. Yeah, that's your H0. They haven't given you any instruction to make your H1 directional, so keep it simple, keep it non-directional. Okay, more information. Also assume that we took a sample of EOR students. Okay, now this is our study. N equals 100, and we find a sample mean happiness of 7. Okay, so do you see what it's starting to do here? We have this previously known population average, which is 6. We now have a current sample mean, which is 7. We're trying to see, is 7 different enough from 6 to warrant saying that 6 is no longer valid as the population average? Okay. So we have to run our Z-test to know this. And as you can see, they've given us all the information we need for our formula. They'll give us our population mean, because we need it for the hypothesis. They will give us our sample mean. They will give us population SD, because this is a Z-test. And they'll give us N. Lovely. And here you can see, if you want to do your standard error first, you're more than welcome to. Or it's just embedded in the formula. You put all your values into the Z formula and you get a Z value of 2.5. Okay, lovely. Oh, how much did I put in? Okay. So before, what you did was, with the sampling distribution and the Z transformation, you got a Z value, say it's 2.5, and you went looking for a percentage to be able to answer a probability question, right? Okay. Well, now we're not going to do it. We're not going to use this Z value for that. We're going to leave it. We leave it alone. We calculate 2.5 and we leave it alone. Now we need to go looking for a critical value so that we can compare our critical versus the obtained. How do we find critical? This is where your alpha comes in, your 5% alpha. So notice it's a percentage. Alpha is 5%. So now you're starting with a percent. You're going into the Z table looking for a percent, and you're trying to match it with a Z value. So it's almost like you're going in the opposite direction as you were before. I'm going to show you the Z table in a second. Here we go. So what I told you about, if we have a non-directional H1, that means we have to allow for both sides to be possible. So our alpha is 5%, and we have to divide it in half so that we can put 2.5% in both tails, and they add up to 5% in total, right? So when we go looking in the Z table, we're actually looking for 2.5%, not 5%. Okay. And where are we looking? In which column? We're looking in the C column. Always, always the C column. Why? The C column was area beyond Z in tail. Our alpha always sits in the tails, okay? Because the rejection region is far away from the population mean. Okay, so 2.5%, we find it, and we need to match it with a Z value in the A column, and that is 1.96. Okay. Now, if we have a directional H1, okay, that means that, say, for example, population average is greater than 6, so we specify the right-hand side, it's greater. And then there's no need to divide the alpha because we're putting all of our eggs in one basket, full alpha on one side. So in that case, we would look for 5%, not 2.5%. So 5% is in this side of the C column, and that would correspond with the Z value of 1.65. Okay, why am I showing you both of these critical values, the possibilities? Well, we know that we always use an alpha of 5% for our tests, right? It's always 5%. So if you're doing a one sample Z test and you have a non-directional H1, your critical value is always going to be 1.96. Because you're starting at 5%, you're dividing it in half, you're looking for 2.5%, it's going to be 1.96 every single time. Same applies for the directional H1. No matter what, your alpha is still going to be 5%. So for directional, your critical value is going to be 1.65. So you can always look for your 2.5% and your 5% if you want to in the Z table, but you can also just study that the only two possible critical values for one sample Z test are 1.96 and 1.65. Okay. Is anyone confused about this so far?
I am.
Okay. What's
Um, yeah, I don't. So the value is always either 1.96 or 1.65, but like, yeah, you just explained this, but I don't really get how to choose or like
Okay.
how do you get there? How do you
Okay.
I don't get the 20, what is it, 2.5% or 4.95% or
Okay. So it all starts with your H1. If your H1 is non-directional or directional.
mm-hmm.
So when it's non-directional, I think I'm going to go back to the slide where I actually show this, just so that it's a bit more visual. Here. When you've got a non-directional H1, that means that you are putting your alpha in both sides, both tails, because you have to account for the possibility that it could be in the left tail or it could be in the right tail.
Yeah.
There's no direction, right? So because of that, you have to take your alpha of 5%, because 5% is the standard, right, that we use.
Mm-hmm.
And you have to divide it in half and put 2.5% in each tail.
Oh, yeah.
So on both sides.
Yeah.
So when you have a non-directional, when you look for your critical value, you're going to be looking for 2.5% in the table and 5%.
Okay.
So that's the whole spiel here with finding the 2.5%, which corresponds with the 1.96 critical.
Okay.
And then the alternative is if your H1 is directional, right? Because in that case, you don't need to account for both sides. You can put your full alpha in one side. And that means instead of dividing it, you're just going to use the full 5%. And do you see how with the percentages here, you've got 0.0495, which if you round up is 5%. And that is more accurate to 5% than the one above it.
Yeah. Okay,
Yeah.
I get it.
Yeah. So basically, this is the non-directional critical value. and this is the directional critical value.
Okay, I get it. Thank you.
Cool. All right, let me go back to the previous slide. Okay, so you've got your obtained that you calculated 2.5, and because it's non-directional, we have our critical of 1.96. Then you compare them. If your obtained is greater than your critical, you reject. Okay, is 2.5 a larger number than 1.96? Yes, it is. So we would reject this H0 and accept the H1, that the population average happiness is not 6. Okay, that is the full process. So it's hypotheses. Make sure to check if your H1 needs to be directional or non-directional. Yeah. Then calculate your obtained value. Go looking in the table for your critical value, and then compare them. If obtained is greater than critical, reject. And by the way, guys, just so you don't get confused, this dividing an alpha in half business, this only applies to our Z table. And it's because of the way the Z table is organized. So I wrote it here on the side. The Z table doesn't differentiate, but like on its own, between the one-tailed and the two-tailed, right? Directional, non-directional. The T table does differentiate. So basically the T table doesn't require you to do anything like that. You can just choose one-tailed or two-tailed and you're good to go. So only the Z table is this necessary. Okay, if you want to look at it visually, okay, so 1.96, and because it's symmetrical, negative 1.96 represent the point where the rejection region begins. Oh, yes, Laura.
Sorry, I didn't want to interrupt, but I can also ask it if when you're done explaining this. However.
Okay. All right. So our sample mean for this example that we just did was 7, right? So I told you we were trying to figure out where is 7, like on this. Oh, I think it's not this side on that. Okay, here we go. M equals 7. So what we just found, the old population mean of 6 was in the center, and we found the sample mean of 7 to be sitting all the way out here inside the rejection region. Okay, so this is telling you that the sample mean of 7 was so far away from this population mean that this population mean cannot be true anymore, which is why we rejected it. Okay, and that's what I wanted to say about that. Laura, does that answer anything for you? Or do you want to ask a question?
I wanted to ask something different. So we use the one sample t-test if we have one interval ratio variable, right? And then also if the standard deviation is known, right?
Do you mean the z-test or the t-test? Because you said the t-test.
I mean z-test.
Z-test, yes, correct. So it's
okay.
One variable, interval ratio, and the test of significance keywords should accompany it. So statistically significant or hypothesis or anything that points towards inferential stats.
Okay, thanks.
Sure. All right.
And so, sorry, can I add on to that?
Oh, yeah, of course.
So the basically the keywords for, if I understand it right, for the t-test and the z-test are the same. The only difference is when the standard deviation is given or not.
Yes, exactly.
Okay, perfect. Then I got it.
Yeah. These two are like identical, pretty much.
Okay.
Yeah.
Perfect. Thank
it
you.
all comes down to that SD.
Okay.
Yes. Okay. What was I trying to tell you with this slide? How important is it? If H0 is true, 95% of the Z obtained of all samples would fall between a critical value. Yeah. Okay, yes, that's true. Okay, so basically, if our sample mean, if it fell between your critical value, so in this white area here, that would mean that H0 is still true. Okay, it means that that H0 is still likely to be true if the sample mean is close enough to it. Okay, and because if it falls outside into this rejection region, that means the probability of getting a sample mean of 7 is so small, it's less than 2.5% chance of getting that sample mean. That just indicates that if the probability is that small, then it probably means that the old population mean is not valid. Okay. That's what I wanted to say. It's basically just repetition. Okay, so we're going to do the same example, same values, but we're going to change n. N used to be 100, and now it's going to be 10. And what do we know about when sample size changes? Okay, if we're dealing with a smaller sample size, right, that means we're going to reduce our ability to generalize. Okay, it's going to be harder to reject H0 because we do not have a big enough sample size. So let's see what happens mathematically. Okay, everything else is exactly the same. Okay, mu is the same, sample mean is the same, sigma is the same, n is changed. We calculate our z value. And before we had a z value of 2.5, and now it's 0.79. Our critical value is 1.96, same. But now when we compare them, our obtained is now smaller than the critical, which means we do not reject H0. So what this is trying to show you, when sample size decreases, okay, it becomes harder to reject H0 because your standard error starts increasing. Does that make sense to everybody? Thanks. Cool. How are we doing? We're doing fine. Awesome. Oh my gosh, there's even more. So, in case you didn't understand it earlier, when you have non-directional H1, this is what your normal distribution would look like with your alpha in both sides. When you have a directional H1, it's all on one side. Okay, so directional is also referred to as one-tailed because everything's in one tail. Okay. So this is a little bit of theory that's linked to your tests. We're mostly concerned with not making a type 1 error. Okay, so your type 1 error is here, is when if you reject the H0, but you shouldn't have. The H0 is actually true. So what we use to avoid the type 1 error is the alpha of 5%. Remember I said that the alpha of 5% is a 95% guarantee of accuracy. So it's like a protection against a type 1 error. Okay. And the alpha can change in different disciplines, by the way. So depending on how accurate you actually need to be or what the consequences are for making a type 1 error in different disciplines. So like in psychology, in the medical field, your alpha becomes 1%. So basically it's a 99% guarantee of accuracy because the consequences of falsely rejecting an H0 are much greater than the social sciences, right? If you're doing medical research and you falsely reject an H0, that can have big ramifications, whereas because of people's health. In social sciences, it's not that deep, so the alpha is 5%. Okay, all that spiel. And then there's also a type 2 error, which is just the opposite. It's when you retain the H0, but you should have rejected it. And that's not such a big deal because remember the H0 is based on previous research. So the H0 is already well supported by research. So if you retain it when you were supposed to reject it, you're basically just agreeing with research that has already come before you. So it's not a big deal. It's the type 1 error. That's the problem. Okay, your one sample t-test, finally. It is almost identical to your z-test. Your key differences, okay, we do not know the population SD. So we must use the sample SD if it's given to us, because some questions, they do give it to us. Or they will give you sample data and you have to use your standard deviation formula to calculate it yourself. And of course, instead of the Z table, we're going to look into the T table to find our critical value. Okay. So if you have a look at your T formula, it's same, but different, right? The only difference is that sigma now has a little hat on top. And that means that we are estimating the population SD. And we're not really estimating it, we're just using sample SD in reality. Okay. So there's your SD formula, which you're very familiar with all the Pearson's R. And for your T table, now, if you look at it, you can see that it differentiates between one-tailed and two-tailed, something the Z table does not do. So when you're picking your values based on, when you're picking your values based on your H1 being directional or non-directional, okay? Well, basically you can just choose proportion in one tail or proportion in two tails combined. So one tail is directional, two tails non-directional. Okay. And because your alpha is always going to be 5%, you literally can just select 5% or 5%. Nothing special. And once you've selected the correct column, then you will match the number to the degree of freedom. And for the t-test, your degree of freedom is n-1. Easy peasy. Okay, let's look at this little example here. Let us assume that we know that 10 years ago, the population of Dutch students spent an average of 1.5 hours per day on reading books. Okay, your one variable, number of hours spent reading books. Okay, what's your units of analysis? The Dutch students. And previous research from 10 years ago is telling you that the population average is 1.5 hours. Okay, so you know your H0 immediately. Population average, hours spent per day reading is 1.5. Okay, let's see if they give any other information. Yes, okay, lovely. Based on recent knowledge, we hypothesize that students today spend less time reading books. Okay. This is the kind of language that indicates you need to make H1 directional. Okay, so it is going to be population average hours reading books is less than 1.5. So very early on in the text of the question, you will have everything you need for your hypotheses. Okay, what's next? We draw a small random sample amongst Dutch students, n equals 100, and find the sample mean is 1 hour. And the sample SD is 0.5. Okay, so this is an example where they do give you an SD, but they specifically give you sample SD, not population SD. Okay, and you have, that means you have everything you need for your formula. Okay, sample mean is 1 hour. Mu is 1.5. SD is 0.5. And your N is 100. Sorted. You can put everything into your formula and calculate your T obtained. Okay, your T obtained is -10. And I told you, when you have a test statistic that's negative like that, we just treat it as 10. Okay, cool. We need to find our critical value. Okay. When we go into the T table, we're going to find a critical value of 1.66, which, let me see if I can find it for you actually on this slide. Okay. Oh, I know what. Okay, so it's not on this particular T table, but our degree of freedom would be 100 minus 1, which is 99. And if we have a look at the T table, Actually, I'm going to have to open the t-table to show you this, maybe during the practice time. But basically, you just match your degree of freedom. Because this is directional, we would be choosing proportion in one tail, and our alpha is 0.05. So it would be this column here, and we'd match it with the degree of freedom. Okay, critical of 1.66. Our T obtained is 10. Is that greater than 1.66? Yes, it is. So we would reject that H0. And our conclusion is, in the population, because we always have to say that, we can assume that Dutch students today, on average, spend less than 1.5 hours per day on reading books. So do you see that conclusion is literally just restating your H1? Okay. Any questions so far about the one sample t-test?
Could you just show the what is it again? No. Standard deviation formula again? Just so I can write it down right now. I don't have
sure.
the
It is in your
paper.
formula sheet as
Yeah.
well. But
I'm gonna forget to write it down later to
okay.
practice.
Yeah.
Oh yeah, perfect. Okay, cool. Yes, thank you.
Perfect. Julia, you're unmuted. Did I do that to you? No? Okay, before I do this, I actually do want to show you the t-table quickly to get this critical value. Something in the chat. Oh, okay. Cool. Let me just open the t-table. Okay. Okay, so this is your t-table. And if you remember from that example, our degree of freedom was 100 minus 1, which is 99. Okay, so if you look at the degree of freedom column, and we keep going all the way to the bottom, you'll notice that from 30, it starts to jump. So 30, 40, 60, 120, and infinity. Okay, so because we have a degree of freedom of 99, we actually just have to choose the degree of freedom that is closest to 99, which in this case would be 120. Okay, so when we match the number, we're going to be looking at the 120 row, and we wanted proportion in one tail 5%, so we're looking at this column. And as you can see, 1.658 was the critical, which you can round up to 1.66, as you saw on the slide. Okay, some of you have seen this before. So this is what your one sample t-test looks like in SPSS output. You cannot do or see the one sample z-test in output. It's just not done, only the t-test. Okay, what's important? Your test value, circled in green. Okay, that is the number that appears in your hypotheses. That is the previously known population average. Okay, your sample mean, okay, from your new study will be up here with your sample statistics. Okay, so the sample mean was 60.55. So basically you're comparing this mean against 52. Right, your t value, which represents the t obtained, 3.624. Okay. And of course, your p-value. Now you've got to choose your one-sided or your two-sided p depending on your H1. Was it directional or non-directional? Okay. So in this case, in this particular example, they do have a directional H1. If you look at the last sentence, the research team have reason to believe the freedom of the press in Africa has improved and is now higher than 52. So it's directional as higher. So basically we would choose the one-sided p-value and it's lower than alpha, so we would reject the H0 in this case. But basically what I'm showing you is that they could only provide you with output and nothing else, okay? And you need to be able to formulate your hypotheses just from looking at this, and you would look to the test value to form your hypotheses. You can already see it says one sample test, so you should know your basic structure. Okay, and then once you form your hypotheses based on the test value, you go straight to your p-value, and you can reject or retain H0. Pretty straightforward, actually. Okay, how are we doing? We're doing okay. Okay, now based on this output, okay, you see our T obtained was 3.624. Oh, Laura, yes.
How do I know again if if I need to look for one-sided or two-sided p? I know that I need to decide whether or not the H1 is directional or not, but how would I know if they only give me the output if I need which one I need, you know?
Yeah, very good question. If they only give you the output and nothing else, you have to assume it's non-directional. So the only time you make it directional is if they give you information that's any kind of instruction, right? So yeah, that's what you would do. Only output, you have to assume non-directional.
Okay, thanks. Yeah.
Okay, so if we're doing this the way we did the hand calculation one, so we've got our T obtained from the output is here, okay, and our critical would be marked here, and basically because our p-value was lower than alpha, and it was extremely low, it was less than 0.001, that means that our T is actually, our sample mean is all the way deep, deep, deep in the rejection region. So that's what it means when alpha is this low. Okay, because if alpha is 2.5% here, then to be less than 0.001 is like way out here. And in this case, 3.624 would be greater than the critical. So we would reject H0 in both situations. I'm just drawing the connection between how we do it in hand calculation versus how we do it in SPSS. Any questions on this before we head into our practice session? Julia? Julia, if you're talking, we can't hear you. But I do see you're unmuted. Maybe put it in the chat. I'll check the chat in a second. All right. If there are no questions at this point, then we can go into practice. All right, guys, I want you to read this and you tell me, of all the different calculations and things we've done today, which one is it and why? Okay, something in the chat. Okay, so the sampling error is only for the sampling distribution of means, and everything else is with the estimated standard deviation, because I was always confused to separate these. Okay. I'm gonna quickly, sorry guys, stop reading. We're gonna go back a little. Let's go back to the formula. So Julianne, if you look at the T formula, even though it's sigma hat, right, means it's an estimate of population SD, that the bottom of the fraction is still standard deviation divided by the square root of n. So the standard error is still there in the formula. Remember what I said, that it's always embedded in the formula. It's not usually done separately. So it doesn't matter whether it's sample SD, population SD, yada, that is the standard error. Did I answer your question? Let me read the question again. What do you mean, and everything else is with the estimated standard deviation? Because for a one sample z-test, we don't estimate the standard deviation. We're given the population standard deviation. So yeah, in fact, same thing with the sampling distribution of means, because it's also z. Whenever we're working with z means we have been given population SD. So that's true for Z transformation. It's true for, okay, you understood it, cool. Yeah, true for Z transformation. It's true for the sampling distribution of means, and it's true for the one sample Z test. It's only in the T test now where we're estimating the SD. Cool, let's go back to practice. Okay. Read it and tell me what's going on in this question. Okay, Laura, give it a go.
I would think it's the one sample t-test because we don't know the standard deviation.
Okay. Why else?
Also because it's based on prior research, which is a test of significance then. And yeah, that we are given a sample, like a new sample size and average.
Okay, so yeah, you're right. You're totally right. So the indicators that I wanted you to really mention, like you're completely correct. We are not given the population SD in this, which means we're working with T for sure. But the fact that the questions themselves, so these 1, 2, 3, which test of significance formulate the hypotheses. Okay, this tells you this is a test of significance. Cool. And how many variables are involved? Only the one. How is it measured? As a ratio variable. Okay, so all of these things point towards the one sample t-test. Okay, so as long as you're recognizing that, and you can even see from the text that it tells you that, yeah, based on prior knowledge, we know that the average sleep is 8.4 hours. And we think today that it's going to be less than 8.4 hours on average. So what are we doing? We're testing a new population mean, a new sample mean against an old population mean. Alrighty, go for it. Answer the question. And can you please give me an indication when you're done? So something in the chat or unmute yourself or something. I'm going to turn my camera off. I'm much more organized with the solutions today, by the way. So every solution is on the next slide when you're ready.
Sorry, can I ask a question?
Absolutely, go for it.
So I've did the formula, but I kind of forgot what to do with the degree of freedom. Because
Okay.
I have a value for t now,
Mm-hmm.
but I thought like in the df row in the t table,
Mm-hmm.
I had to look for then the closest number to my answer and then look at the proportion in 1 till and then 0.05.
Yes.
But then what is the degree of freedom? Because it says in the formula sheet, it says it's n minus 1.
Exactly. That's what it is. So what is your n in this question?
5.
Right. So 5 minus 1 is 4. So your degree of freedom is 4. So that you look at the row 4 and you match it with the column, the correct column that you
Oh,
chose.
wait, that is also indeed the row I would use according to my answer.
Yeah.
So like my T answer. Oh, okay.
Yeah.
I hadn't looked at it like that yet. Okay, thank you.
Sure. Guys, don't forget, if you're done, please just put something in the chat. Just say done in the chat so I know.
Can I just ask something real quick?
Yeah, of course.
So how was it again? If the T obtained is larger than T critical, we reject HO.
Yes.
Okay, thank you.
Amy and Laura, I haven't gotten your done yet. Are you guys done? Can we move on? Lovely. Okay. So here is your solution. Okay, so your H0 should have been in the population. Teenagers sleep on average 8.4 hours per night. And your H1 should be in the population. Teenagers sleep on average less than 8.4 hours per night. Your sample mean should have been 6.92. Your standard deviation should have been 2. Okay. Your T obtained should be negative 1.65, and your T critical should be 2.13. So because our obtained is smaller than the critical, we would retain H0. Okay, so your conclusion would be that in the population, teenagers sleep on average 8.4 hours per night. Give me a thumbs up if you got all of that correct. Lovely. Everyone else, thumbs up.
I got it wrong, but I did something weird, I think, with the what is the thingy with the I forget the names of the, is it the standard deviation? The O with the cap on.
Oh, yes. Okay, the standard deviation. Yeah.
Yeah, I think I filled some wrong numbers because I got the mean right, and
Okay.
but I probably did something weird on my calculator or something, like the steps I did right. But
Okay. So what I would ask you to do when you have a bit of time during the practice time is just to redo that standard deviation calculation, just to find where you made the mistake. Yeah.
okay.
Okay. Cool. We're going to move on to question 2 in the meantime. All right. A research team is investigating how popular summer music festivals are amongst young people aged 18 to 35. This population of young people is normally distributed with a mean number of festivals attended of 1.6 and an SD of 0.9. If the researchers took a random sample of 25 young people, what is the probability that their sample mean would fall between 2 and 2.2? Okay, talk to me, guys. What about this stands out to you? Anyone want to try this?
Yeah. So I see that the population is normally distributed, and it asks what is the probability.
Yeah. Okay, so
And
tell me from that, just that, what is the probability? What are the possibilities now?
the Z transformation and this or sampling distribution of means.
Correct.
Just,
Okay.
and
How do we
then
narrow it down? Okay, Laurie, raise your hand.
I think it's the Z transformation because we have the SD known.
Because we have the what, sorry?
The standard deviation known.
We do know the population SD, correct? But remember, that is true for all Z things. And the sampling distribution of means is also working with Z. So that doesn't narrow anything down. So it's, if you think about the two things, right? Z transformation and sampling distribution of means is a key word in sampling distribution, right? The key word there is sample. Okay. If we read this, it's more about the keywords that are there that are usually not there when we do a Z transformation. So we're reading so far up until SD of 0.9, it could be either one. Okay. If the researchers took a random sample of 25 young people, N equals 25. So they give you N, and they start talking about taking a sample from the population, not randomly selecting an individual, randomly selecting a sample. What is the probability that the sample mean would be between 2 and 2.2? Remember, so we're not speaking about a specific number of festivals attended, like for a specific case. We're talking about a mean number of festivals attended. So this would be a sampling distribution of means, not a Z transformation. Okay, so if it mentions sample mean, it gives you N, it's the sampling distribution. Okay, is that clear for everybody? Kaz, I'm back. We've got a question in the chat. Which column from the Z table do I use in this case? Okay, so very important. First step when you get these probability questions is to draw the distribution. Okay, so draw it, mark the area. Our population mean in the center would be 1.6. Okay, so if you mark the area between 2 and 2.2, you should be able to see that that area does not touch the mean at all, but it also does not go into the tail. Okay, so that is one of the special situations that I told you about where we have to subtract, right? And whenever we are doing something special, like adding and subtracting percentages, it's always B column. Okay. Does that answer your question? Don't forget to say done in the chat when you're done. Yeah. Okay, I think I'm going to show you the solution now. If you're not done, you can always finish it later, but here we go. Okay, so this is what your drawing should have looked like, something like that, okay? And so because you've got your two sample mean values to use, so you've got 2 and you've got 2.2, you would have done your sample distribution of means formula twice, gotten two separate z-values, found two separate percentages in the B column. And because this is a subtraction situation, you would take the larger one, subtract the smaller one, and get a probability of 1.28%. Did we get this one right, guys? Good to know. And then your conclusion, which I didn't include on the solution, but remember, conclusion is very important. Okay, I would just repeat as much of this as you can. So, if the researchers took a random sample of 25 young people, n equals 25, the probability that their sample mean would fall between 2 and 2.2 is 1.28%. So literally just write it all out again, but give the probability. Okay. Awesome. Let's go on to the next question. All right. Based on prior research, the researchers know that this population, look, the same values, same variables before. This population distribution has a mean of 1.6 and an SD of 0.9, same. When the researchers take a sample of 25 young people, they find a sample mean of 1.9 musical festivals attended. Which test of significance should you use and why? Okay, you tell me.
Do you hear me this time?
I do, yes.
Oh, okay.
Okay.
I would think it's one of the one sample tests because they indicate that they want an HO and an H1, and also they ask for a test of significance. And then I would think, because they say that the population distribution has a standard deviation of 0.9, I would say that it's the sample Z test.
Perfect. No notes. Go for it. Hey guys, are we done yet? Just let me know. Okay, perfect. Remember, guys, you need to communicate with me, otherwise I don't know. Don't know if you're finished or not. Alrighty, let's look at the solution. Okay, so pretty straightforward. You get your Z value, your Z obtained of 1.67. Your Z critical is 1.96, very predictable because it's in non-directional H1. Your obtained value is smaller than your critical, so again, you would retain your H0. Did anybody get anything different? Okay. I'm feeling like we're all good here. Lovely. Okay. Ready for the next one? Give me a thumbs up. I think you're ready. Okay, let's go again. Give this one a read and then unmute yourself and let me know what you think we should do with this.
I think it's one of the first ones, so the Z transformation or the sampling distribution.
Absolutely. What tells you that?
It's asking for what is the chance.
Exactly.
And I see that there's no mention of. Wait, is there a mention of sample mean? Wait.
In the actual question.
Yeah, so the 8.4 hours is that's the mean then, right? Not the sample mean.
It's the population mean, yes.
Yeah, okay, so then I think it's the Z transformation.
It is a Z transformation. So when I say in the actual question, I actually just mean this very last sentence. What is the chance that a randomly selected teenager from this population will sleep between 9 and 10 hours? So in that sentence, nothing about obtaining a sample mean, right? Notice it talks about a randomly selected teenager, okay, an individual from the population. Okay, that points to the Z transformation. If it is randomly selecting a sample mean or a sample from the population, the other one, okay? So Z transformation, go for it. All right, looks like we're ready for a solution for this one. Okay, this is what your drawing should have looked like. Again, it's a subtraction question. You've got your two Z transformation formulas, your two Z values, and your two percentages, large one minus the small percentage. Your final one should be 21.67%. So there is a 21.67% chance that a randomly selected teenager from this population sleeps between 9 and 10 hours per night. Give me a thumbs up if all this went really well. This is good to see, guys. This is boding very well. Okay. I believe this is the final question that I have for you to do. So your week 4 exercise 2, question 1. And then if there's any time left, then you can go back to your old assignments from week 3 and week 4 if you want to keep looking out for the stuff we've done today. But yeah, let's do this. All right, guys, are we finished with this one? Ready to look at the solution? I won't give you the solution until you tell me you're done. Okay. Sorry, Laura, I see you. Okay. Almost. Okay. I'll give you like a minute or two. Okay, lovely. And Luke. Okay, so these are the percentages that you should have calculated going in columns. And then when you compared across, you should see that Instagram was the most successful platform for selling this product. So your conclusion should look something like this. In the sample, people who saw the ad on Instagram were most likely to buy the product. Those who saw it on Facebook and YouTube respectively were similarly likely to buy it. Okay. But I think the most important conclusion here is definitely that if you saw it on Instagram, you were most likely to buy it. Okay. Everyone comfortable with this question? Comfortable with the conclusion as well? Give me a thumbs up. You did the wrong exercise. No. Oh no. Which one did you do, Julie?
I did. I thought it said exercise 2. Is this like the second? Oh, this is the second exercise we did.
Oh yeah, week 4
Yeah.
exercise question 1, yeah.
Yeah, so I did exercise 2 in this document.
Oh, okay. Out of
But-
curiosity, what was the question?
I think it's just a one sample t-test.
Okay. Was it SPSS or was it
No, it's by hand.
is that by hand? Okay, well you know
Yeah.
extra practice for the t-test.
Yeah, sure. Oops.
All right, cool. So guys, that's it for today. What I'd like you to do before our session on Saturday, which remember is now going to be 3.5 hours, a little bit longer, is I'd like you to just take a look through your week 1 through 4 assignments / exercises, and your practice exercises that they gave you over the Christmas period. So I just want you to look at all of those and see how comfortable you feel reading those questions now that we've had this training, and actually point out to yourself where you're now spotting the keywords and things, okay? And if you have any problems with any of those questions, when you do read over them, bring them to me on Saturday, okay? Before we go, only based on the content we've done so far, because now we're halfway through the course in terms of content. How are you feeling about what we've already done on a scale from 0 to 10? You can put it in the chat. Oh gosh, what just happened there? Sorry guys, I have no idea what just happened. Okay, we're back. All right. Let's see. Okay. 7s and 8s. Can I ask some of the people who've put a 7? Because I'm only asking for weeks 1 through 4. What's making you say 7 and not higher? Like, where are you still feeling a little bit insecure? Just so that I can work on it for the next 2 sessions. Yeah, Julie?
I think for me, a little bit like I don't want to overestimate myself. And also like I get it now, but I do have to practice a bit more myself to really be sure which test to pick. So now I have to look at my notes before I can pick a test. But I
Okay.
like so I have to practice a bit more. But that's
Okay.
that's on me, not on you. I love your explanations. It's super helpful.
Okay, good.
Yeah.
Good. Yeah, like you said, practice is the only way that you can get better at this course. It really is. So that's part of why I also want you to go back and just look at every single exercise that you've ever been given for this stuff and just do it over and over again until you know, want to die. That's when you know you've practiced enough. Alrighty. I hope you have a good evening, guys, and I'll see you Saturday.
Thank you.
Thank you. Bye.
Bye bye.
Bye.
Cheers, guys.